Hey guys, this video is about rate laws, and rate laws are a little bit different than anything else you've ever done in chemistry. So pay attention, it's not hard, it's just different. Okay, so a rate law expresses how the rate is dependent on the concentration of the reactants. So if you think about it, how fast or slow a reaction occurs is going to be dependent upon how much of the reactants you have in the solution. So these are technically, what we're going to be looking at today are technically called differential rate laws, but we usually just shorten it to rate law. And there's something called an integrated rate law, so don't get those two things confused. And we're going to talk about integrated rate laws in the next video. So only reactants are used in the rate laws. This is because we only consider the forward direction of the reaction, but I like to think of it as it's the only part of the reaction that we really have control over. We don't have control over the products. We can put more reactant in, we can take reactant out, but we cannot control how much product is in there unless we're removing product as the reaction goes forward, which is something we'll talk about in a later unit. But for this one, okay, if this is the reaction, A goes to B, then the differential rate law would look like this. So the only reactant here is A, so we put it in brackets showing that the concentration of A, little k is called the rate constant, and it's really, really important. And rate constants can vary widely in their numerical value because of the various rates of reactions. Some are very slow, which would have a very, very small rate constant, and some are very, very big, which would have a very big rate constant. Therefore, rate constants can vary widely. You need to keep that in mind, okay? And then that's going to be equal to the rate. Okay, and then this little guy up here is really important, and that's what we're going to be looking for in the majority of the time in the video. It is called the order of the reaction with respect to the reactant that it's sitting on. So that would be the order of the reaction with respect to A. So in other words, that number changes based on how this reactant affects the rate. Okay, and it'll make more sense as we do problems, but I just wanted to put like a definition out there for those of you that need that to learn. Okay, so in this reaction right here, in the second reaction, the only reactant here is NO2, and so NO2 is the only reactant in the rate law. This little n is the order of the reaction with respect to NO2. K is our rate constant, and then we have rate. Okay, so, and then the last one, we've got two reactants this time, so they're both in the rate law. This is ammonium, one of the reactants, and then this little n is the order of the reaction with respect to ammonium. And then this little m is the order of the reaction with respect to nitrate. So they use different letters. It doesn't really matter what letter you put up there. It's just a placeholder right now. It's just a variable. All right. And then K is the rate constant for that reaction. And then we have rate. Now, the order of the reaction can only be found through experimentation. It cannot be found any other way. So we have to look at the data from an experiment. All right. And then right here, since we have two reactants and they each have their own order, the overall order of the reaction can be found by taking the sum of all of the orders. No, that's complicated. It's really not. It's very easy. All right, so first example. All right, we have this reaction right here, and we did the experiment, we did the reaction 3 different times, and each time we did the reaction, we started with a different amount of ammonium and nitrite. The first time we did it, we had 0.1 of ammonium and 0.005 molar of nitrite. The second time it was 0.1 and 0.01. The third time it was 0.2 and 0.01. So the first time I work one of these questions, I'm going to show you how they show you to do it in a textbook, and then I'm going to show you a shortcut, because sometimes we have students that don't want to work these problems because it takes so much paper and pencil work. So I'm going to show you both ways, and the first time is going to be the long way. All right? So first we have to find the rate law. So I'm going to write a pseudo rate law, or a rate law with just the bare bones, what we know. So rate is equal to K times the concentration of NH4 raised to the N times the concentration of NO2 minus raised to the M. Right, so that was on the previous slide. And in order to complete this rate law, we really need to know what N and M are. So I have to find this from this experimental data. So N and M from lab data, okay? And so this is the lab data that we got. In order to find N, I need to look at the lab data where ammonium changes, but nitrite is staying constant. If I look at 1 and 2, ammonium's not changing. Nitrite is changing, so that's not going to work. If I look at 1 and 3, ammonium is changing and nitrite is changing, so that's not going to work. If I look at 2 and 3, ammonium is changing, nitrite is staying constant. So that means that any change in the rate is 100% due to the change in concentration of ammonium, because this isn't being changed, so it can't affect the rate. So I am going to compare experiments 2 and 3, and I am going to put experiment 3 on the top because it's got bigger numbers in it. So I'm going to put 3 over experiment 2, and this is just for our viewing. It's not part of the math. So I'm going to plug in all of the information into our rate law that we wrote over here. So my rate for the third experiment is 5.40 times 10 to the negative 7, and that is going to be equal to K, we don't know what K is, times the NH4 concentration of 0.2 raised to the N, times the nitrite concentration of 0.010 raised to the M. And then I'm going to divide that by the second experiment. So that would be a rate equal to 2.70 times 10 to the negative 7 is equal to K times the concentration of ammonium of 0.1 raised to the N times 0.010 raised to the M. All right, and so this is a method taught in algebra, I think algebra 2, where you take two equations with two different variables to determine their values. I don't remember what it's called. I do remember it's not called substitution, but that's about as much as I remember. Okay, so we have 0.010 raised to the M and 0.010 raised to the M. So those two things cancel out. The K's cancel out because no matter what they are, they're the same. And so if I take 5.4 times 10 to the negative 7 and divide it by 2.7 times 10 to the negative 7, I get the value of 2. And that would be equal to 2 raised to the N. And so my N value has to be 1. So that means that this is first order. That's how we say that. So right now my rate law is rate is equal to K times NH4 plus raised to the first power. So there's just a 1 there, and you don't have to write it just like in math. All right. And now to find the value of M, okay, for nitrite, we have to look at 2 experiments in which the ammonium is not changing because we don't want it to affect the rate, but the nitrite should be changing because we do want it to affect the rate. So if I look at experiments 1 and 2 here, okay, ammonium is 0.1 and ammonium is 0.1, so it's looking good. Nitrite is 0.005 and nitrite is 0.01. So the change in concentration here of nitrite is the only change that's occurring, and it's directly affecting the rate. It's the only thing affecting the rate. So if I do the same thing, and this time I'm going to put experiment 2 over experiment 1 because the values for experiment 2 are bigger and I don't want fractions in this. You can do it with fractions. You have to use the logarithm rules for the experiments. But just make it easier on yourself. So I have 2.70 times 10 to the negative 7 is equal to K times the concentration of NH4, which is 0.1, raised to the first, times 0.01. Now we're going to put that over 1.35 times 10 to the negative 7, so we're just plugging everything into the rate law again. And ammonium's not changing, but nitrite is 0.005 raised to the m. Okay, so again, we get 2 is equal to, let me cancel out this stuff, so K cancels, 0.1 raised to the first, 0.1 raised to the first cancels, and then that's going to be equal to 2 to the m, because 0.01 divided by 0.005 is 2, so m is also 1. So then for my rate law, I would have nitrite to the first as well. So this is my rate law that it wanted. Okay, and the order of the reaction with respect to ammonium is 1, and the order of the reaction with respect to nitrite is 1. The overall order is just those two together. So overall, the order is 1 plus 1, so that means the overall order is 2. All right, now before I find the value of K and its units, I want to show you a different way to do this that is way easier, and I'm just going to show you with the first ammonium. Okay, so let me get rid of all this stuff. All right, and you don't have to write all this out. You can if you want to. If it makes you feel comfortable, go for it. But for those of you that are a little more lazy, I'm going to show you an easy way to do it. All right, so we look at our data and we do the same thing. We say, okay, we have to use experiment 2 and experiment 3 for ammonium. And if I look right here, this doubles, so times 2. And then if I look right here, this doubles as well, times 2. So my rate, right, this is our rate law. Rate is equal to K times the concentration of NH4 raised to the N, concentration of NO2 raised to the M. So my rate doubles, so I plug a 2 in for rate. I know my K's are going to cancel, and then my NH4 doubles, and it's raised to the M, and I know my nitrites are going to cancel because they're the same value. So I end up getting this, and it's just M is equal to 1. So that was a lot easier. That's how I'm going to work them in the rest of the video, but you can always plug them into the rate laws and divide them out if it makes you feel good about it. All right, so now to find the value of the rate constant and its units, we're going to take one of the experiments. I usually pick the first one, and I'm going to plug it in to this rate law, right? So I've got 1.3, I'm just going to take experiment 1 and plug it right into the rate law. So I've got 1.35 times 10 to the negative 7 molarity per second. It says I need units, so I'm going to start putting units in here. K is what I'm looking for, and then NH4 is 0.1 molar, and nitrite is 0.005 molar. And so to find K, I'm going to divide both sides by the product of these two, and the product of these two is 0.0005, and we've got molarity squared. So this cancels out right here. One of the molarities is going to cancel out, and I'm going to take 1.35 times 10 to the negative 7 and divide it by 0.005, and I get that my K is equal to 2.7 times 10 to the negative 4th, and since one of the molarities canceled out, I end up with 1 over molarity times the second. So one of the molarities is still there, and it's in the denominator. All right, so that's the value of the rate constant here. So this unit can be written several different ways. I usually write it like that, but you can also see it written molarity inverse, seconds inverse, or I think this is more of an old school way to write it, where they write liters over moles because it's the inverse of molarity times a second. All right, so that one's a little bit weirder, but all of these mean the same thing. All right, so let's do a couple more examples. The following reaction was performed 4 separate times and the data in the table was collected. So first we want to find the rate law. Before I should do this, I should probably write rate is going to be equal to K, and I've got bromate raised to the N, bromide raised to the M, and hydrogen ion raised to the P. So to find N for bromate, I am going to look at first experiment 1 and 2 and make sure that everything else is staying constant, because that can't be changing if we want to know how bromate affects the rate law. This negative ion should be up here, not down here. All right, so this one right here doubles. This bromide is staying constant here and here. Hydrogen is staying constant here and here. So that works for bromate. So this one is doubling, and this one is also doubling. So the rate is doubling, so I'm going to plug that in for rate. So 2 is equal to, and then the concentration of bromate is doubling. So 2 is the concentration of bromate. The K would cancel out, the bromide would cancel out, and the hydrogen ion would cancel out. So that means that N is equal to 1. You'll find that first order is the most common. All right, so N is equal to 1. Now for the next one, for bromide, which experiments am I going to use for bromide? I have to make sure that bromate is constant, not changing, and hydrogen is constant, not changing. So in the next one, if I look at experiments 2 and 3, bromate is 0.2 and 0.2, so it's not changing. Hydrogen is 0.1 and 0.1, so it's not changing. And bromide is 0.1 and 0.2. So looking here, this is doubling. This is not changing at all, so it's times 1. So my rate is 1, and that's going to be equal to 2, because my concentration doubled, raised to the M. And my K will cancel, my bromate concentration will cancel, and so will my hydrogen ion. So M is equal to 0, because 2 to the 0 gives you 1. And then for my last one, for hydrogen, I need to find 2 experiments that I can use where bromide and bromate are both staying constant. So if you look at the data table, can't use 3 and 4 because both bromate and bromide are changing. I can't use 2 and 4 because bromate is changing. The only ones that I can use is 1 and 4, because that's where bromide is staying constant and bromate is staying constant. So if I look at this one, hydrogen is going from 0.1 to 0.2, so that's times 2. And the rate is going from 8 times 10 to the negative 4th to 3.2 times 10 to the negative 3rd. So that is actually times 4. So my rate is increasing by 4, and then my concentration is doubling. So 2 to the P is equal to 4, so that means that P is equal to 2. So my order with respect to bromate is 1, bromide is 0, and to hydrogen is 2. So if I'm going to write the rate law, it would look like rate is equal to K times bromate, and there's only 1. And then bromide disappears completely because it's 0 order, and anything raised to the 0 is 1. And then hydrogen to the 2nd power. So the overall order is 1 plus 2. And then to find the value of the rate constant and its units, I'm going to plug experiment 1 in and then solve for K. So K ends up being 0.8 1 over molarity squared times the second. So this time our units for K are different. And on the AP test, most of the time the units of K is worth a point on the free response or open-ended response, and the value for K is worth a point. So these units are worth the time to get. All right, another example. Okay, so I need to find the rate law. Rate is equal to K times NO times CL2, and this is N and this would be M. So if I look at NO, the only one that I can use is this one. So this doubles. Chloride is staying the same. And this one right here quadruples about. So I would have rate is 4 is equal to, everything else cancels, 2 to the N. And so N is equal to 2. And then for chlorine, I can use this one because my nitrogen monoxide is staying constant. And right here doubles, and this doubles. So I would have 2 is equal to 2 to the M, and so M is equal to 1. So then if I plug everything in and solve for the rate constant, my answer is 180. 1 over molarity squared times a minute, because now we have minutes here in this rate law instead of seconds. All right, last example, and I'm going to go pretty quickly. Okay, so we want to determine the rate law. Okay, so for S208, I am going to use experiment 3 and 1 from here to here. This is staying constant. This is changing by 2. This is changing by 2. So N is equal to 1. And then for the second one, I'm going to use 2 and 1. So this doubles, so M is also equal to 1. So my overall order is 2. My rate law, rate is equal to K S208 times I. Both are first order. And then the value of the rate constant, I'm going to plug the first experiment in. So I get 3.9 times 10 to the negative third, 1 over molarity times the second as my K. All right, that's it.